Okay, this will work. Okay, language and evolution. These two fields have intertwined history. As many of you know, historical linguistics, in particular the history of Indo-European languages, directly inspired Darwin and to work out the theory of natural selection. I have a quote here. I won't read it. I assume you're all familiar with it. But since then, I think the biology and linguistics have developed very far along. But I think nowadays biology probably has a higher prestige than linguistics. That's somewhat unfortunate. And one of the reasons, I think, is that evolution biology has made tremendous progress because it laid out a mathematical or quantum foundation of biological change. That is the theory of population genetics. Okay? Linguistics has also made a lot of progress. We now have very predictive models of linguistic structures, but we haven't really developed a comparable set of mathematical theories of change. And that's sort of what I want to do here. Phylogenetic methods have been applied to language sometimes with great fanfare, but it's interesting to note that the very earliest methods developed for phylogenetics actually came out of quantitative studies of historical linguistics by the work of Peter Buhlmann in the 1970s. As was well known, when you use those methods, you have this property of junk in and junk out. If you don't give those algorithms sufficiently good data, you get ridiculous results. Some recent exchanges in science have shown very vividly. Okay, so what I want to show today is the following. I want to develop a set of models for language change that addresses the issue of language variation and change, of course. And the point here is that are there any general principles of language change? And if so, are these properties of UG or interfaces or something even more general? So that's one goal. The other goal is to develop something like the modern synthesis of language change. And this is very much like the population genetics research. And so this is different from phylogenetics. Phylogenetics, if you take the output of language change, you try to infer what, how languages are related. The models of change I'm more interested in is that we take what's known about language and about language acquisition, about language processing. We try to come up with models that can predict language change, or in more realistic terms, how we can explain why some attested changes are actually inevitable. Okay. This is a very familiar picture that guides the intuition between to study the parallels between biological change and language change. I won't dwell on this. You have a grammar, and you talk, and that's the input to the next generation, and you learn, and then you go on. Okay. If you look at historical linguistics broadly, you see two kinds of changes. One is very familiar. The other is actually quite recent, quite recently discovered. Okay. One kind of change is that, as in many cases of syntactic and morphological change, language users are essentially bilingual. You have two competing systems, if you will, and that can be viewed as the probability distribution of, say, two grammars. So that distribution changes over time, and in many cases, the change can drag out for hundreds or possibly even 1,000 years. It's apparently in some cases in what order change in classical Chinese. And this is something that we get to understand a little better more recently, thanks largely to the work initiated by my colleague, Bill Lebov. Phonemic change can happen very rapidly. I'll show you some dramatic examples, sometimes 2 or 3 years. Okay? And so this is something, you can think of this as the learner is exposed to a mixture of two different phonemic systems, and they learn one of them rather than learning a probabilistic distribution over the two. And that makes sense. There's no penalty in having a rule of two different ways of saying the same thing, but it is somewhat peculiar to assume you have half of a phoneme, right? So here's a classical case of gradual change in syntax. So here you see a single speaker is essentially bilingual, having a info final and also info medial grammar on two adjacent sentences in a text. This is more recent, at least more recently discovered, phonemic change. There's a very famous variety of American dialects called the cod merger. I have this merger, so for me the two vowels are the same. But the two vowels here, for many speakers of American English, are different. They're certainly different in the UK. But many speakers of American English actually treat the two vowels the same thing. The very interesting fact of this is this has happened at adjacent areas. So Massachusetts is a very solidly merged area. So if you're in Boston, the two vowels are the same. But in Rhode Island has traditionally been a distinct system. So there, the two vowels of cod and cod are actually different. Okay, Dan Johnson, a recent graduate at Penn, went to some of the neighboring towns, and he found that if you take, so this is one family. So if you take the parents and you take the F1 and F2 measures and take the absolute value of the difference, you can see they're very, very different. And that's even true for teenagers. But if you look at a 9-year-old, the two vowels are essentially the same. Okay, so I hope you can hear the audio. Okay. Okay, so here's Tom.
Cod. Cod.
Sorry.
Cod. Cod.
Different? Here's the mother.
Cod. Cod.
Different. Here's the older sibling.
Cod. Cod.
Here's the younger one.
Cod. Cod.
Okay? This happens in 2 or 3 years. So you really are seeing two different kinds of change patterns. That's presumably ultimately due to the differences in syntactic and phonemic systems. So this is what I'm going to do today. Today I'm going to try to develop a model of change via through transmission that more or less functions like the basic model of natural selection. And then we'll look at one particular case of the change in word ordering, extending some earlier work, the change in word order in French. That takes a long time to work. And then also a more recent one, namely this cod merger. In both cases, we'll show that you can actually predict when the change is going to occur, how long it's going to take the change to actuate in the population, and eventually why this change had to occur. Okay, and this is interesting. Many years ago, I offered a class on the evolution of language when I was teaching at Yale, and the first time I offered it, the first day, 350 people showed up, and then I showed them the equation of mathematical biology, and only 60 people stayed. But we have to do this, okay, because otherwise we're not even in the game. Okay. So here's the basic model of natural selection. Let's say you have two genes or two competing variants, call them big A and small a. It could be red eye or green eye, in fruit fly. And they make up the proportion of P and Q in a population, so percentage of P and Q. And let's say, for whatever reason, the red eye, big A is slightly better. Okay, and let's say it has a fitness of 1 or 1 minus S. By which I mean, in nature, the fitness differential is usually very small, but this is something you can do in a lab. You can blast them with a gamma ray and measure the body counts afterwards, or you can go out in a natural environment and count the frequencies of those variants after a drought or after rain and so on. So that's something you can quantify. As we'll see, we'll do the same for language. And then you basically develop the model of change mathematically. It's very interesting that these models were developed well before we understood anything about the genetic structure. Because we're talking about genes in very abstract terms, and it worked. I think by the same token, we can actually talk about parameters abstractly and still get the models to work, even though we may not know exactly what those parameters actually are. Okay, so here's the basic model of natural selection. You have in one generation, they're at the proportion of P and Q. And then after selection, of their fitness being 1 and 1 minus S, you got big A being P, but small a being Q minus S. So clearly Q is going to get smaller. And next generation would be simply you rewrite this equation, right? And if you plot this curve over time, you get this beautiful S-shaped curve. And that's the basic model for natural selection. As we'll see, that's basic model, this basic pattern of language change as well. So what we need to do here is, instead of having this very abstract or biological model of transmission, we actually put linguistics into it and put the language acquisition process into this transmission process. So this is something I developed when I was in graduate school, something called variational learning. It has to take the following form. Let's say the learner has two grammars, big A and small a, and they have probability of P and Q in their minds. And these grammars may be innate. These grammars may be constructed. It doesn't matter for the mathematics to go through. And if you hear a token, an input token in the environment, you pick big A with a probability P, you pick small a with a probability Q, and afterwards you try to see if it works. If it works for the input token, you increase its probability by some amount, and otherwise, if one guy goes up, the other guy would have to come down. If it doesn't work, you penalize it by decreasing its probability. I should say that this is a very general learning scheme. These guys are actually behaviorists. They use this to model how rats run mazes. Okay, so this is a very general learning process, and I won't dwell on the details here, but it has some utility in accounting for parameter setting. But that's not for today. Okay, so what's the notion of fitness in this scheme, in this competition-based learning scheme? Well, that's very easy to do, for a linguist. So that's something you can quantify. The probability with which a grammar clashes with the input. So what's the probability of a grammar fails in the particular linguistic environment? That's something that we linguists can estimate in a corpora. Okay, so let's say the learner is juggling between the V2 grammar and SVO grammar, and if you're trying to see how those two grammars fare in an SVO environment, you simply count the percentage of sentences that will be consistent with one and inconsistent, with the other. You got two numbers. That's between 0 and 1. Okay, so let's say these numbers are C of big A and C of small a, and this holds. If you let the learner run for a while, this is true. Okay, I won't dwell on the mathematics here. So after you let your running go for a while, the learner converges on a stable combination of two grammars, and the two grammars, the weights are exactly specified by how likely is a grammar penalized in the environment. Okay, so in most cases that we study, we have cases of language acquisition. You assume there's a more or less monolingual environment. So you have a target grammar, you have a pretender. Okay, the target grammar never fails by definition. The pretender fails some of the time. So, so one of those values is going to be 0 for the target, and the other one would be non-zero. So it's clear to see that the target grammar will have a probability of 1. After learning, you learn a grammar. That's a general case. That's a special case. But if the language environment is heterogeneous, this is typically the case in language change, well, then they will converge to a stable combination of the two within one generation. Okay, and that's language change, right? So the question is that, of course, when you have a homogeneous environment, you need the environment to be altered in order for change to happen, right? So it's a very interesting question to see how some new variant is introduced. It could be language contact. It could be learning error. It could be anything. That's what's known as the actuation problem in historical linguistics. That's not something we can usually answer, okay? Because who knows what happened 600 years ago. But this is something we can answer, is that what happens after some new variant has been introduced? Can we predict whether this new variant can knock out the old one, or this new variant will peter out after a while? And that's the basic model here. Okay, so let's say you have one generation of speakers, and they are essentially bilingual. They have grammar A with probability P, and grammar big A probability P, small a with probability Q, and they talk. Okay, and let's assume that the two grammars are not necessarily mutually exclusive. Let's say they have something in common. That there are some sentences that are mutually compatible. So English and German SVO sentences are fine for both, right? But let's say big A has some probability of producing a sentence that small a cannot, handle, and small a has some probability of beta producing some expression that big A cannot, handle. because these weights are P and Q, so therefore the probability of a big A being penalized is going to be exactly the probability of the speaker choosing small a and the speaker producing a token that big A cannot handle, so that's beta times Q, and also this is alpha times P. Okay, so what are alpha? Well, what is alpha and what is beta? That's essentially a monolingual corpus. So you look at the monolingual corpus of big A. You count what's the percentage of sentences that big A can produce that contradicts small a, and that's something that we can all do. Okay, so once you redo this, you calculate the penalty probability of those two variants. You rewrite the probabilities of P in the next generation following the equation I showed earlier. You get something like this. Okay, P prime equals P over something else, and this is exactly the equation I showed you earlier from natural selection. Now, if you rewrite S as alpha minus beta over alpha. Okay, so one thing that's clear is that if big A produces, on average, has produces a higher percentage of tokens that small a cannot handle, counting monolingual corpora, and then big A will always going to kill small a. Okay, so we can now, in principle, we can say we merge any two grammars together. We can take the two monolingual, corpora and count, and then it makes a prediction. Now the question is, are these predictions true? Okay, so if we plot this out, of course, you get this S-shaped curve, and that's not surprising because we saw the same S-shaped curve in natural selection. Of course, this is something that's observed over and over in the history of, in a study of historical linguistics. And this is, you can go, you can go a little deeper. You can actually estimate how many generations it takes for some change to go from very few in the environment to completion. I won't dwell on the algebra here. This is actually quite straightforward. Is that as long as you can calculate S, as long as you can measure alpha and beta, which will give you S, you can assume in the beginning a new variant is very rare, 1%, and the other guy is 99%. But after some time, the new variant is now almost all there is to it, and the old variant is now at 0.01. And you do this, you can actually estimate the number of generations for change to take place. And that's, of course, as you can imagine, is going to be a function of how better the new guy is compared to the old guy, right? If the new guy is much better than the old guy, it'll kill the old guy faster. So we'll make use of those equations later on. So now the empirical stuff. Okay, so here's a well-known, very well-studied case in historical linguistics that has to do with the change of word order in the history of French. So French was a V2 language, no longer a V2 language nowadays, so that's modern, not okay. Old French is okay. And also Old French was a non-subject language, it was pro-drop language. It's no longer the case now. Okay, so we like to know why it changed. So what's the competition here? So it went from a V2 grammar to a SVO grammar. So these are the two variants that are in competition. Following the logic I was sketching out, we can go estimate and the alpha and beta in monolingual corpora of V2 and SVO languages. So we take something like German or English. It doesn't really matter. You found that actually, historically speaking, 70% of the V2 languages produce expression of SVO. So these are just fine with the SVO grammar. It's the sentences like with a verb in the post verbal position that's going to clash with the SVO grammar. That's about 30%. So this is our alpha. Okay. Now what's beta? So what's the percentage of SVO sentences that are in SVO languages, or the sentences produced by SVO grammar that are inconsistent with the V2 grammar? Oh, that's easy to do. We count, English, I counted childish, I counted, Wall Street Journal, not huge amount of difference, is that whenever you have a verb in a non-second position, that's when the V2 grammar fails, right? So SVO is certainly fine for both grammars. So that's our beta. So we have alpha being 30% and beta being 10%. So alpha is greater than beta. So that means that change from V2 to SVO shouldn't be possible, because V2 is better than SVO when they are put in put in a competition, and that's contrary to the facts. So something else is going on. So what's going on? Well, we should keep in mind that French was a pro-drop language. Okay, so if the subject pronoun is dropped, okay, you get something like this would be a sentence that's usually inconsistent with SVO grammar. But if you drop the subject pronoun, it becomes XV. That's consistent with SVO grammar as long as you allow pro-drop, right? So this is the case of you can post it in the empty category, either to left or right side of the verb. Now, of course, if you have an SVO sentence, if you give it pro-drop, well, then it actually would amplify the advantage of SVO grammar over V2, because if you drop the subject, the sentence becomes V1, which is transparently not V2. Okay? So between the two factors of this double whammy, SVO grammar is going to lose out to the the V2 grammar is going to lose out to the SVO grammar. And this is roughly how we do this. Okay, so you have subjects. Sometimes they're pronouns. Sometimes they're lexical NPs. We don't have to worry about that. When you have a pronoun, when you have a pro-drop language, you have a chance of being dropped. So the probability of you dropping this would be having a pro-drop would be A times D, right? Then this I won't bore you, with all the details. Basically, you see if you happen to be a lexical NP. The subject stays. This still goes against SVO grammar, but crucially here, if you drop the pro, this is no longer inconsistent with SVO grammar. You do the same for the green guys, namely, what happens to SVO if you add pro drop to it, and you change the numbers here slightly. Again, this is pretty straightforward, algebra. We don't have to worry about it, A and D. So now these are revised fitness values of V2 and pro-drop on the one hand, and SVO and pro-drop on the other hand. So these are the real grammars that are going through competition. So this will show that loss of V2 would happen if alpha prime from the previous slides is greater than beta prime. If you do solve the equation there, you see that if A times D is greater than about 18%, then the V2 grammar will necessarily lose to an SVO grammar. Okay? But what is A times D? Well, remember A times D is the percentage of pro-drop in Old French. Okay, if you look at the text in 14th century French compiled from Ian Roberts' book, you see that there's over 40% of pro-drop patterns of the time at the time. Okay, so this is clearly greater than 18%. So that means that the loss of V2 in French to SVO was necessary. Okay, and this actually I think makes a novel prediction as far as I know it's true. That is that all Western Romance languages had V2, had V2 order. All of them lost it. Some of them, and all of them that lost pro-drop, lost V2 had pro-drop. Some of them still have pro-drop, like Italian or Spanish. So this is actually a prediction you can make on numerical grounds. Okay, I didn't know, I still don't know French, old or new, but that's a prediction you can make by only looking at the numerical basis of competition between grammars. We can go slightly further. Okay, so we calculate now. This is just it's just rewriting what I had earlier, and we can calculate S, which is now since we know the percentage of now subjects is about 42% from E.M. Roberts' data, we can rewrite S as 0.6. So we can actually estimate the number of generations we expect to take for V2 to lose out to SVO. And that's about 10 generations. Okay, so I don't know how long do you want to attribute a generation to the ancestors, the French. But let's say roughly 20 to 30 years. So that means that we expect it to take about 200 to 300 years for the change to go to completion. That's more or less correct. Again, that's a prediction you can make on numerical ground. So it's crucial here for the story to work that the loss of pro-drop took place later in the history of French. So after V2 was lost, because otherwise it would not be possible. Okay, that's indeed the case because pro-drop actually was lost about 2 centuries after V2 was completely gone. Okay? So these are, I think, illustrates a set of changes for which the outcome was entirely predictable on the basis of the intrinsic properties of grammar and the numerical tabulation of how often they contradict each other. Okay, so here you could say we're predicting change. Now let's look at the other case I was alluding to. So that change took a few centuries, right? This one took place in probably 3 to 5 years. Let's again try to hear this. And this is the diagram from the distribution of cod-cod merger in North America. The green areas are areas in which the 2 vowel variants are the same, and these areas are the dots are the 2 vowels are actually different. So you go to New York City, you can clearly hear the 2 vowels being different. So here's a student of ours who's from Boston.
I pronounce caught the same as caught.
Okay, so this is a guy that actually says the 2 vowels are the same thing. Why mergers are interesting? Well, mergers are very interesting, I think, historically, of course, but also more generally. Mergers happen. Mergers are probably the most documented instance of language change in all studies. Okay, and that poses an interesting challenge to the view that language functions or changes to facilitate communication. Why would you make 2 words that previously sound different and make them the same? But this happens all the time, which has actually led to Bill evolve to the very strongly anti-functionalist position to language change. Right, and also mergers are generally below the conscious social linguistic evaluation. Okay, so there's some language variation that are quite stigmatized. So you can say that what makes them change is more complex. But these are actually things that are usually below people's awareness. So that gives us a good opportunity to study the factors governing the change from an internal point of view rather than a social point of view, which is hard to quantify. And mergers and phonemic systems in general are quite fairly early. This is a study, again, in Leboeuf's work and an extension of his work showing that basically if you don't move to an area by the age of 6 or 7, you have no chance of picking up the really deep regional features of the phonemic system. And as I said, mergers are among the best documented changes on record. Reversals of mergers are extremely rare, if it ever happens at all. Okay, very often you see an area where it had 2 vowels merged into 1. You rarely see a case of an area at one time had 2 vowels merged into 1 and go back to 2. That, as far as we know, rarely, if ever, happens. We like to account for that. Okay. So this is Dan Johnson's work. It's a very detailed sociolinguistic work that should be made. It should be part of the literature language acquisition. Okay. So there's a case of I have to resort to colors here because for me the 2 vowels are the same. So this is the O in D-O-N, so the male name. And this is A-W, the vowel in D-A-W-N, the female name. And in Boston, the 2 vowels are more or less merged to the D-A-W-N sound. Okay. But Rhode Island, as I said, initially had the 2 vowels being the same. Being different. But around late 80s and 1990s, there's a lot of migration going from this area to here, largely due to job opportunities. Okay, so as a result, the change is spreading from Boston to Rhode Island or the Rhode Island dialect regions, and as is shown earlier, in some families, older siblings still retain their parents' distinct system, but the younger children are actually acquired the newer system. This all happened in the span of 3 to 5 years. So this has to be learning from peers, namely children with a vowel system except at home, namely usually learning from their parents, would interact with the children from a different dialectal background and learn their system. And this is clearly a case of influence due to migration. So what we're interested in is that what kind of population mixture would it trigger a deep change of the sort that we're seeing in the span of 3 to 5 years? Just to hear this again, if you're not convinced, I was really stunned when I first heard this because I didn't imagine change would happen so rapidly.
caught, caught,
caught, caught, caught, caught, caught, caught,
Okay, the last one again being the youngest speaker. Okay, so children usually learn their parents' distinct system at home because that's where they're primarily picking up their language. So let's call this the M- system. So if you paid attention to the previous slide, or to slides further back, the 3-year-olds actually pattern like their parents. But once they grow up to be in a school environment, they're actually going to pattern like their peers. Then they run into kids that some of them would be speaking this M+ system, namely the merger has taken place, and they're going to be learning from a mixture of P0 and Q0. Okay, and then according to the dynamics of competition we had earlier, we need to calculate what's the probability of the merger system failing in this mixture, and what's the probability of the distinct system failing in this mixture, and that allow us to calculate the expected rate of P, namely the weight of the merger system after learning. And since this is a case where apparently children adopt one system rather than having a mixture of two, we're going to pick the one that has a higher value to be the one, namely the one that's better. If you're better, you actually kill the other competitor instantly in one generation rather than letting the competition drag on for many years. Again, this is probably fundamentally related to the difference between morphology and syntax on the one hand, and phonology and phonemes on the other, as lots of psycholinguistic and neurolinguistic evidence show. Even for fully fluent bilinguals that require two languages at birth, one phonemic system appears to be somewhat more dominant. Okay, so how are we going to define fitness? One of the easy ways to do so is to say, well, let's calculate when the two dialects are merged together. Let's see what's the probability of leading to miscommunication. So Bill Leboeuf has been tracking this for about 30 years, and he reported about 80 cases in a span of 25 years. It's not a whole lot of them, and this is typical. Okay, Gillian Sankoff, my colleague, is from Montreal. In all of Canada, the two vowels are the same. Bill Leboeuf is from New Jersey, and that he has, and that area had a system where the two vowels are different. So here's not a typical conversation, but an amusing one. Gillian said it would be even better if Don could take her to the airport. So Don is Don Wrench, a historical linguist in our department. But when this thing was said, it was about 20 years ago. We had a female graduate student in the department by the name of D-A-W-N, who was actually blind. So Bill Leboeuf clearly understood D-O-N to be D-A-W-N, and was wondering why a blind person could take anyone to the airport. Okay, so this is actually a genuine case of misunderstanding. If you look at the rates of errors that Bill collected over the years, they found that actually it's people who have a distinct system that are more easily confused than people with a merger system, by the ratio of 4-to-1. We have something to say about that later on. And the more general consideration, I think, is actually not gross miscommunication, because that happens rarely. 40 instances, 80 instances in 25 years is not a lot. In most cases, you can figure out what the other person is trying to say. So I think here the general consideration is actually the ambiguity introduced by competing phonemic systems and the confusion they introduce at a very temporal, at a temporal scale, very subliminal, that could actually mislead people. And so this will be something similar to garden path in syntax, but this will be garden path in phonological processing. And there are a variety of psycholinguistic evidence supporting this view. This is one of the earliest studies by David Sweeney, showing that highly influential, showing lexical processing at the very initial stage of language processing is highly autonomous. Contextual cues coming much later. By later, I mean later by 100 milliseconds, but not 5 seconds. So here's an example. Rumor has it that for years, the government building had been plagued with problems. The man was not surprised when he discovered several spiders, roaches, and other bugs in a courtroom, in a corner room. So bug, of course, is ambiguous. It could either mean the insect or spy. Okay, so this is not actually what they did with cross-modal priming paradigm. The subject heard the sentence, but as soon as at the time when bug was uttered, they showed pictures of either insect or recording device as in a spy sense, and speakers actually show equal amount of activation. So that means that when you hear the word bug, even though the context makes very clear, you cannot possibly be talking about the recording device. The recording device meaning is still activated. Of course, very quickly you figure out that you're talking about the insect. And some of the more direct evidence comes from more recent work. I won't go through all the details there, but here's a particularly important one. Speakers, or rather listeners, show slowdown as well as errors when they process sentences like, "She saw him duck and stumble near the barn." Well, this is very interesting because duck is two ducks, right? One is the noun form of the duck, the other is the verb form of the duck. Duck being a noun is much more frequent than duck being a verb. So people actually were interpreting initially of duck being a noun. This is why they have slowdown, because that wouldn't make any grammatical sense, even though the preceding context is very clear. This cannot possibly be a noun. Okay, so this suggests when we process homophones, we actually go for the more frequent form first. Okay, so this is even true regardless of even part of speech. Okay, because you should be having a verb here, but you actually hear a noun first. So what this means is the following. If you're in Boston, if you have the merger for caught and caught, if I say something, I slap on the caught. If you have only one vowel, you're actually going to hear the past tense of catch first before you hear the noun form of caught. This is exactly what these results show. This will give us a way to calculate the fitness of the two competing phonemic systems. Okay, so now we have a combination of, let's say you have the speaker, the environment consists of some people saying the merger, some people not saying the merger. The learner sometimes will try out the merger system, sometimes will try out the distinct system, so you have 4 possibilities. And what's interesting here is that we're going to calculate the expected probability of a particular phonemic system misleading the learner, however subminimally, temporarily, and we're going to calculate the probabilities and calculate the penalty probabilities, and then we'll see that one that's penalized less is going to win. Okay, the crucial data here is actually are the homophones that may result from the caught merger, things like these. I won't read them out for you. So we can estimate the frequencies of these words as reliably as we want. And I tried several different frequency counts. They don't seem to matter very much. So here's one scenario. Okay, so this is what happens if the learner is trying to merger, a system, namely the system under which the caught and caught are the same. Sometimes it's going to hear speakers using the merger. Sometimes it's going to hear speakers not using the merger, namely using the distinct system. Let's just say, without loss of any generality, let's assume DON to be more frequent than DAWN. So what I mean by here is that if the merger speaker is saying dong as intending to mean dong, okay, and if you are using the merger phoneme system, you're going to hear the two words to be the same. And because DON is more frequent than DWN, so it's actually intended to be DON, you will be right. But if it's intended to be DAWN, you will be wrong. Okay, because DON is more frequent than DWN. This is also the case here. So here, even though the speaker is producing potentially two acoustically distinct words, you can only hear one of them because you have the merger, or you're trying out the merger. So again, even though the sound of DON is actually different from DAWN, but when it's intended, you would get it right because you always hear the more frequent one first. So therefore, if you use the merger system, the probability of you failing would be the smaller of the frequencies of those minimal pairs over all minimal pairs. So that's the expected probability of failing when you have a merger system. Now the unmerged system is different. It's somewhat more complex. So you hear two vowels. You hear O and also AW, but they're actually psychoacoustically confusable to some extent. So this goes back to Peterson and Barney. Roughly, AW can be perceived as O with probability of 1, with 0.1, and this goes the other way as probability of 0.6. So this needs a little more thinking. So here you can hear two vowels, okay? And again, you sometimes hear from merger speakers. Sometimes you hear from distinct speakers. So here's if you hear from merger speaker and DA, that sometimes is intended to be DON, sometimes intended to be DAWN. And here, but again, those two vowels have been merged by the merger speaker, so the two words are acoustically the same. Okay, so you actually hear DON. You actually hear DAWN because this is an area where O and AW have merged to AW. So basically, if you actually mishear AW as O, you actually guess right. Okay, so if you actually mishear AW as O, you actually, when it's intended to be Dong, the male name, you're actually okay. Otherwise, of course, you fail. So all the rest is about the same. You can plug in all those numbers. All those are presumably constants. We assume the psychoacoustic confusability are inherent properties of the speech and also perception system. We assume them to be constant. We also assume word frequencies to be constant. So what you have here is is interesting. So the penalty probability of the distinct system is actually going to be a function of the frequencies of speakers, merger speakers in the environment. So compare this with the previous slide here. So this is a constant. So this is only a function of word frequencies. But the next slide shows that this is the fitness of the merger of the distinct system is actually going to be a function of what's the percentage of merger speakers you have in the environment. All the frequencies here are constants because we're talking about the frequencies of words. So this in biology is known as something as frequency independent selection, namely the fitness of competing variants is a function of their frequencies. It typically happens, say, in very common in competition when you in a population with very few males. Initially, they may have a huge advantage, but as the number of males increase, then their fitness value would go down because the competition gets more fierce. It could be also other sort of resource driven competition. So unlike the French case where alpha and beta are constants, here the fitness values are actually sensitive to their frequencies. So therefore, we can actually calculate what's the percentage of P0, what's the value of P0 such that C minus is going to be greater than C plus. To solve that equation, that's going to tell us the exact percentage of merger speakers in a population that's going to make the merger kill the distinct system. It's a linear equation, so it's easy to solve. It's 22%. Okay, so this is calculated only on the basis of word frequency and acoustic measures of vowel confusability. So that means that if you have over 20% of kids in the environment that speak the merger, everybody will learn the merger. If you have a frequency of under 22% of the kids in the environment that speak the merger, then those kids would actually lose a merger to the distinct, to the distinct system. This is actually what happened, believe it or not. So Dan Johnson, in his very careful study interviewing thousands of subjects, described 3 stages. First stage is not many merged parents in a community. Small number of merged children will learn the distinction from their peers. And second stage, more merged parents have moved in. The proportion of natively merged children entering the peer group, not enough to stop natively distinct children remaining distinct. Finally, the proportion of native merged children exceed Y. He posted a threshold. And while distinct children may not be in a minority, they have enough contact with merged peers that they lose their inherited distinction. So it's 22%. So let's see if this is right. the towns that he's looking at, some of them reached the threshold, reached stage 3, namely everybody became merged. Some of them by 1990, some of them by 2000. 2000 he actually got the data for, got the demographic data for, as I show here. What he found is that children, he said, he noted that children with one merged parent, one distinct parent, were usually merged. This would not be surprising because it's 22%. If you primarily learn from your parents, and you only need 20% of the tokens be coming from the merged parent, that's enough for you to learn the merger. Let's assume that one of the parent isn't exactly mute, and that's enough for this generalization to be true. In his school survey, this is what I thought was pretty compelling. So he went to the exact time when went to the school board and found the demographic data of where they were born, the children were born, exactly the time when merger knocked out the distinct system. He found that at the time the percentage of children from the Boston area was at 18 to 23%, which is very similar to the 22% that we have calculated on purely on numerical basis. Okay, this is more advanced here. Of course, this is the things already taking place, and you have, of course, you have a higher ratio of merged kids. And more broadly, this also accounts for the asymmetry of errors in Lebov's natural miscommunication studies. In most cases, you hear a slap on the cot, you hear past tense of catch. In many cases, it won't cause any confusion. It's only those rare cases when you happen to know both dong and dong in the same department, you have the confusion. But very interesting is that it's a merger, is people with a distinct system that's more likely to be penalized, more likely to be confused. And this makes sense because if you use a merger system, you're always going to hear the most frequent one. Okay, you only fail when you hear the least frequent one of those minimal pairs. So that inherently gives you an advantage. And this also accounts for the easy, spreadability of the merger. So this is something that you only need a quarter of the population, under a quarter of the population, to sweep out the distinct system. This has been documented both in Massachusetts as well as in Pennsylvania. When we studies of looking at Western Pennsylvania mining towns in the 1920s had traditionally a distinct system. But due to the migrant workers, I think from a Slavic background, who actually learned the merger system in the Boston area, they moved there, and in the span of 10 years, all those towns are actually merged. You only need a small ratio of that. It probably also accounts for that the large cities have been very resistant to the merger because it's easy to move 20 people into a town of 80. It's very difficult to move 2 million people into a city of 10 million. Okay, so it's not impossible. It's just demographically much less likely. And finally, even the mutual confusability of the vowels is not hugely important because, again, if you have a merger system, you only fail when you encounter the least frequent of the minimal pairs. Okay, so here's a case we can look in the South where there's a well-known variation in Southern American English known as a ping-pen merger. So the two vowels are actually now in the South no longer the same. This only happens in front of nasals. Okay, so we have the same dynamics. We do the same calculation by using different set of words, different frequencies, and also different measures of vowel confusability. And we get about 32% of speakers that have the merger would trigger this wholesale change. And we don't have the detailed data on this, but this is work from dialect surveys from the 1800s and also early 1900s. You can see it started out very flat, then it just shot up. Okay, so this we can't exactly say this is actually 33%, but this was triggered by this feature has always been a rural dialect feature, but when around this time people were starting to move into big cities, and even a small fraction of the speakers can actually lead to massive changes. So in a span of about 30 years, the entire South changed from the distinct system to the merger system. Okay, I should wrap things up. What we want to conclude today, I think in a narrow sense, is that we like to study biolinguistics, and to do that we have to study biology quite seriously. And biology relies on quantitative models. So we have to develop quantitative models that make predictions. Right? And of course that's what linguists have been doing all along. And models, of course, can guide work on language variation and change and processing, acquisition and so on, and can sharpen our work. And the models actually here are simple. Okay? Everything I've shown today are really high school, algebra stuff. And even the more advanced topics here were developed by biologists by the 1960s. So there's no new math to do. But it's crucial that we take the linguistic factors into account: how language is processed, how language is learned, how language is also structured. Because otherwise, the model would be toys, and it won't have any empirical content. So this is something I think we might want to say more broadly in the context of language evolution, is that change and variation appear to be governed by learning, and processing. So you can think of UG, came out of Africa, and then we marched it to the places. We have this diversity of languages. At least some of the patterns can be pinned down to the inherent properties of language learning and language processing, and some of them appear to be modular. So the processing of phonological information in lexical processing appears to take place regardless of what the syntax or semantics or pragmatic context is. That really takes, and that's somewhat surprising. Okay? And as also in the case of language learning, I think the model of learning I'm showing you today is derived from mathematical psychology of rodents. So that's a very ancient learning scheme. So it's possible that these are the interface conditions that we entertain, and they may actually tell us something interesting about the diversity and change of languages around us. Thank you.